We're going to talk about calculating the moment of inertia for a couple of the basic shapes. We're going to do thin rod about one end, and then I will assign to you the prospect of doing the thin rod about its center. It only involves changing the limits, so it's not that big a deal. We're going to do the easiest one second, and that is a hoop or a ring. And then we're going to do what you guys are going to find to, I think, I hope some of you find it interesting, but I'm afraid many of you are going to kind of give me that look you always give me when something looks unfamiliar to you. And we're going to do a disc. Now, to appreciate this a little bit, I want to remind you that we've done moment of inertia for point masses. So it is possible to estimate the moment of inertia of a rigid body using the rules of a point mass. And I don't really want to do this because I don't think it really serves a huge function, but I think some of you need to see it just so you have a place to kind of connect this to what you've learned in your calculus class. So I want to start with a rigid body that instead of doing the actual calculation the way we should, we're going to try using what we used in class last week and treat the rigid body as a point mass first. So we'll calculate the moment of inertia by doing a summation. Now, the problem with this is it's going to be wrong. We're going to get the wrong answer. In fact, I'm doing this solely because this is how calculus taught you to do integration. If you think back real briefly to your calculus, let's see if this looks at all familiar. Do you remember doing this? Drawing the little rectangles in there to find the area under the curve? Does it look familiar? And then you went from rectangles below the curve to rectangles above the curve and finding their average. And then you went from rectangles to trapezoids, right? It felt like every week was something new, tedious, and boring. And that's because it takes a little while to convince you that executing an integral can do the same thing as a summation. I mean, the process of integrating does the process of summation. They were trying to show you that these approximations would get you close and that there was always a different way to approximate. We can do the same thing with calculating a moment of inertia. The moment of inertia as a summation is an approximation. It's not the actual moment of inertia. So I want to consider looking at a rod about its end and spinning it around its end. Imagine it's a meter stick. I'm not going to say it's a meter stick. I'm going to say it has length L and mass capital M. You can't read the red, right? And if you guys want to come up front, by all means, I'm supposed to do new seats today. I'm sorry. I will do new seats tomorrow when we're going to have a fire drill. Shh. We don't know a period. It's going to be a surprise. Today was a surprise to me. So, if you imagine a meter stick, imagine that we could take the meter stick and break it up into 10 pieces. So 10 pieces. 1, 2, trying to think of trying to do it evenly, but I doubt I'll be able to do it very evenly. I'll try. 3, 4, 5, 6, 7, 8, 9. That's 11 pieces. I don't want 11 pieces. It's got to be 10. So I'll try one more time. One, 2, 3, 4, 5, 6, 7, 8. There. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. Assume that they're evenly spaced. Clearly they're not. Stop making fun of me. 10 pieces. Now, if I wanted to find the moment of inertia of this system, then I could start by considering that this is I have 10 pieces of equal mass. So each one of those blue dots has a mass of 1/10 m. Now, I'll point out, if I break it up into 10 pieces, there's actually 9 spaces, right? There's 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. So when we start looking at where they are, we have to account for each mass and how far away from the pivot point they are. To do that, the first mass is at 0, so that one's pretty easy to do. I'm going to put 0 squared here. Then I add to it the next mass, 1/10 m, times where it is 1/9 of the way across. So 1/9 L squared. Now the next one still is 1/10 of the mass, and it is 2/9 L. Now, can you kind of predict what this is going to look like? We're going to have 3/9 L, 4/9 L, 5/9 L, all the way to the last piece, which will be located. It'll also have the mass 1/10 m, and will be 9/9 L away. I know I could write that as 1 L. I need to leave it as this so that we can find a simpler way to do the work on this. Now, the first thing I would encourage you to recognize is that every term has an m in it. Every term has a 1/10 in it. And every term has an L in it, even the first term, because 0 times that L is still 0. So I can factor out from all of the terms 1/10 m L squared, because the L's are all squared. Is that okay? No trouble with that? I can factor something else out. Every term has a 9 in the denominator, but it's squared, so I'm going to factor out 1/81. Okay? Now, what's left is 0 squared plus 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared. So that's why I left 9/9 in there, so I could have that. Now, I know some of you math folks know that there's a way to just get this, like with a formula. I never memorized those recursive formulas, so I don't know what it is. I would actually have to grab my calculator and do 9 squared plus 8 squared plus 7 squared plus 6 squared, but luckily I have all of you. So, and I already did it in my notes, but I want you to do it. So here you go. You got to do your 9 squared plus 8 squared plus 7 squared plus 6 squared plus 5 squared plus 4 squared plus 3 squared plus 2 squared plus 1 squared plus 0 squared. 81 plus 64 plus 49 plus 36 plus 25 plus 16 plus 9 plus 4 plus 1. So what do we got? 285? All right. So, the moment of inertia is equal to 285 over 110. Just for fun, can somebody divide both of those by 5? What's 285 divided by 5? Please. 50 what? And 810 divided by 5? 162? I don't think that reduces anymore, but here's the thing, and here's where I'd really like you to pay close attention. The moment of inertia of a rod about its end is a known value. The moment of inertia of a rod about its end is 1/3 ml squared. How close is 57 over 162 to 1/3? I'd say it's pretty close, because 50 over 150 would be 1/3. So what is 57 divided by 162? So you see that we get close. The exact answer is 1/3 ml squared. The summation answer gets us within the ballpark. Now, if we want to get closer, we'd break our mass up into 20 pieces or 100 pieces. But the point of doing the calculus is to find a way for the calculus to do it for us. So today I want to show you how the calculus for this works. And to do that, you first need to know that the moment of inertia is a fixed integral. I should draw like some funky shape to do it like this and say that if it has an axis through some piece, and every piece of this is called is a piece of mass dm located a distance r from the axis. That's how I'm supposed to do it. I'm supposed to say that we have some weird shaped object. Its moment of inertia is a sum of every piece of mass times how far away it is from the axis squared, where dm represents an infinitesimally small piece of mass. But they don't write it like this. They switch and write this as r squared dm, because the order in this calculation doesn't matter. There's no vectors. And more importantly, sometimes m changes with r. You see, there's three things we can't assume. First, we can't assume that our r is uniformly distributed. These mass pieces could be everywhere. Second, we can't assume that the object is uniform. It could have areas that are more dense and areas that are less dense. And we can't assume that they are distributed in any symmetrical way. So that's why there's such a esoteric formula that has really no guidance. Our job is try and figure out a way to actually use that to find the moment of inertia. And generally, there's a couple of things that we do to use this formula to find the moment of inertia. But even on the AP exam, you will know the answer that you are trying to find before you start. So keep in mind, often the problem will say, prove that the moment of inertia of a rod about its end is 1/3 ml squared. And you'll be given the answer. Now they might use that for the rest of the problem, so you won't have to prove it to get the rest of the problem correct, but to get those couple of points at the beginning, that's what they want. So I want to show you how to use this formula, and there are a couple of steps that you should write in that will help. And so let's start with a uniform object. It's going to be the same object we saw before. It is a rod of mass m and length L. We're going to do the problem with an axis about one end. But the truth is, it doesn't really matter where you choose the axis to be. The problem is the same. Where you choose your axis tends to make it so you have to choose your limits. We're going to make two broad assumptions about this. The first assumption is that this object has uniform density. So it's symmetrical, and every piece of the object has the same mass. So, step one, when faced with a problem like this, you're going to need to find a way to describe the mass mathematically. So to start, I would encourage you to pick a place on the object. Draw a square, and that square represents a piece of the mass, dm. It's just one piece of the object. Now, in describing this piece, we need to describe it geometrically. A lot of students don't know what I mean by that, and in the beginning, this is kind of tough. But basically, we need to pick some variables that will help us point to where each piece of mass is. Now, to understand what I'm going to do next, you have to understand that I'm going to use the symmetry here. There's some clear symmetry, meaning I'm not going to say that there's any pieces that are up or down on this rod. I'm going to break the rod up into pieces that are just the same height. So all the pieces will be the same height. What I am going to do is I'm going to say that pieces of mass are a distance x away from the origin, and that every piece of mass is a distance dx wide. I know this seems a little weird in the beginning, but I'm trying to get a way of writing this geometrically. And so I'm using pointers, something that tells me where the piece of mass is. And it's also helping me establish that the first piece of mass is located a distance 0 away from the origin, and the last piece of mass is located a distance L away from the origin. So each piece has a place along the rod. Now, this next thing I'm going to do isn't going to make a whole lot of sense to you the first time you see it, and you won't understand why we're doing it until the end. But remember, I need to describe the mass. But what I'm really doing is building a geometric approach to where each piece is. But I've also described the size of the piece by saying that each piece is dx wide. I'm doing that specifically so that I can use density to my advantage. We're going to come up with a density for our object, a placeholder that's used to describe the density of the entire shape. Now, just be forewarned, in real physics, the reason we do this is because the density doesn't have to be uniform. The density can be something where maybe it gets heavier as it goes to the end, or it gets lighter as it goes to the end, or even something more challenging than that. So often the density can be given to you as a function. So for objects that are not uniform, this might not be a constant. But in this class, at this moment, the densities are going to be a constant. And I'm going to choose a type of density that works for my problem. There are 3 kinds of density. There's linear density, areal density, and volume density. So if anybody's ever played the guitar, they sell guitar strings based on their density, the mass per unit length of the string. This is like a guitar string, meaning it's very long compared to its thickness. So I'm going to write its density in terms of its mass and its length. The symbol we use is lambda for linear density. But it's just a placeholder. The reason we have that placeholder is so that we can write the mass in terms of the size of the piece. The piece is dx long. So lambda times dx represents how much mass that piece has. So I'm writing the mass in terms of the length. I'm doing that for several reasons. First, I need something geometric so that I can point to every piece of mass in order to do my integral. Second, I need a way of incorporating the distance to each mass. Because remember, the moment of inertia, which is what we're attempting to find, is the integral of r squared times dm. R squared is the perpendicular distance It's the perpendicular distance to each piece of mass. And dm is the mass of each piece. So the reason why I needed to write dm in terms of the geometry is because I have to point to the masses. I have to have something I can use to describe where it is. But I also need to have a variable of integration that's in terms of the shape, or else I can't integrate. So that's what all of these steps are about, transforming dm into something that was about the perpendicular distance, which is what I've done. If you look at what I have here, my integral isn't going to use r, I'm going to use x, because x is the perpendicular distance from the axis to where dm is. So I'll replace r with x squared. That's something we'll do a lot. We'll replace the r with some other placeholder that we're using for that distance. And I will replace dm with something that has our variable of integration, something that's based on the shape. So instead of dm, I'll have lambda dx. Now, this is the mass of each piece, and this is the perpendicular distance away. The last thing is to make sure I add up every individual piece. So I have to tell it the limits of my integration. So clearly I'm going to start from the axis, which is 0, and I'm going to go to the end of the rod, which is L away. So this is assembling my integral. The hardest part of this is assembling the integral, bringing all the pieces together that you will have to use in order to successfully execute the integral. Doing the integral should be the easiest part. Assembling the integral is the hardest. So we've assembled the integral. At this point, this is an integral all of you can do. I'm going to go to another page so I have a little more space to work. But I have my I equals the integral 0 to L of x squared lambda dx. The first thing I'll point out is that lambda is a constant. We designed it that way. So I'm going to pull lambda out front. Now the integral of 0 to L of x squared dx. Now this part's pretty easy. Most of you know how to do the polynomial integration because we've talked about it for a while. And all of you who are passing calculus sure as heck better know how to do it. So again, this will be lambda. And when I execute my integral, my antiderivative is 1/3 x cubed. Add 1 to the exponent and then divide by the new exponent. And then apply my limits 0 to L. When I do that, I'll have lambda times 1/3 L cubed minus 1/3 times 0. And now I'm going to bring in and substitute for lambda. I'm going to put in what I based the density upon. the density was m over L times 1/3 L cubed, which you can see pretty clear. One of the L's is going to cancel, leaving me with 1/3 ml squared. Not so bad? We'll see. Again, this was me being pretty heavy-handed. If I was to rate these in terms of easy, medium, hard, this is medium. We're going to see an easy one next, but then we're going to start a hard one. I'm glad I was able to bring about 3/4 of you with me this far. A few of you are drifting into slumber, but you should redo this on your own for the center of the rod. It's good practice. The answer is 1/12 ml squared. You should demonstrate that you can come up with that answer. There's 2 ways to do it. One of them is just to go from the middle of the rod to the end, which would be 0 to L over 2, and then double your answer. One of them is to go from negative L over 2 to positive L over 2. Try one. So I'm giving you something to try. I would encourage it. I only have so many shapes at my disposal. So when I give you a pop quiz on this, I'm kind of telling you what I'm expecting you maybe to think about doing tonight. That way you can't say you were blindsided by it tomorrow when I say, do this for me. All right. I want to do another one. This time I'm going to be a little less involved in it. I'm hoping you guys can help pick up some of these pieces. We're going to do the hoop or the ring. It's considered a thin ring. The answer is mr squared. That's the moment of inertia of a hoop or a ring. We're going to see if we can put all the pieces together to get that answer. First thing I think you should do is I think you should, draw a picture of it. So this is my hoop or ring. I'm going to take a moment and mark the center, because we're going to do this about the center of the object being spun that way. It'd be much harder to have the axis like this. Try and spin it this way. That'd be really hard. For those of you who are smarty smarts, I may be willing to show you how that's done, but it's hard. Now, we're obviously out of time, but over here, this piece of the ring, I'm going to call DM. And I guess I had a similar reaction. But I had a similar reaction, and here's why. Because I had spent what I felt was a 42-minute session with a demo to indicate what the moment of inertia was about. So when I received that information, what is this good for, I was, in fact, a little surprised. But not terribly so, because I've come to expect certain things. And, disappointment is among them. So, I'm going to take a moment just to indicate to all of you who aren't really connecting the dots, because I do understand that one of those dots was before Gasparilla and one of those dots was after, and perhaps in the middle you fried a few things that would have led you from one dot to the next. So let's take a look at what we found yesterday. And not to be too big a jerk, but that is my only mode of operations, is jerk mode. The moment of inertia of a meter stick about its end is 1/3 ml squared, which tells me how difficult this object will be to turn or rotate more importantly, how difficult it will be to change the rotation of this object about its end. So for all of you who thought that was probably a good question, that's the answer. That's what the moment of inertia is. It is how difficult it is to change the rotation of that object about that axis. This is an axis about its end. So let's imagine for just a moment that I set a meter stick on the very edge of a table. That will make the end the pivot point. And I go to let it go. Can we all more or less agree that the meter stick is likely to rotate and pivot about this point? Is that okay? At least it will instantaneously after I release it, which means the very instant after I release it, it will begin to accelerate. Now, it might slide off the table, but at that instant that it's released, it will experience an unbalanced torque. And because it will experience an unbalanced torque, it will begin to accelerate. The amount that it accelerates will be dependent upon its moment of inertia. That's the full statement. I would encourage you to have a statement like that in your notes, something that you can rely on, perhaps when I ask this question tomorrow for 10 points. Now, to put a finer point on it, yes, sir?
Can you say it one more time?
Oh, okay, so it's more important now. Yeah. I'm going to argue that all these things are that important. Okay. If I release this object, it's going to experience an unbalanced torque, which means that the object will change its rotation. It will begin to accelerate. It will have an angular acceleration. The size of that angular acceleration will depend on the object's rotational inertia, its resistance to changes in acceleration. Although it might not accelerate with this acceleration the whole time, it will have an instantaneous acceleration, meaning an acceleration the instant it's released. We can use Newton's second law for torque, which we proved last week, as a means of determining this. I went on at some length to show you how we could go from net force to net torque. I hope you remember that. And from there, we derived that the net torque will be equal to I alpha for an unbalanced torque. The I from yesterday is the I in that equation, the moment of inertia. So I think you have everything at your disposal to come up with an expression for the acceleration. But I fear that you will act like you don't. So I want to start by recognizing that when I release this meter stick and state unequivocally that the pivot point is right here, that there is a single force that will cause a torque about the meter stick. Logan, can you tell me what that force will be? The weight. And where's the weight likely to act on the meter stick? Thank you. I knew I could count on you. In terms of L, this point is located a distance 1/2 L from the axis of rotation. So as I consider the acceleration of the system, the torque will be 1/2 L times mg times, in the instantaneous case, I'll say sine of theta, but I think we can all agree that'll be the sine of 90 degrees. Now, what is the moment of inertia? In this case, the moment of inertia is that value that determines how much the object will accelerate. It's more complicated than just the object's mass. Now, again, you should be able to see quite clearly that there is a means to find the expression for the acceleration of the meter stick. And I'm not trying to be demeaning. I'm trying to make sure that we are all on the same page for what we must do next. That's what good the value of the moment of inertia is. It shows up in 3 places. This is the first. Any question about this example? We can't really follow through with this example, meaning I can't use this alpha to tell me anything. I can't figure out the velocity of the meter stick or how long it takes to reach the ground. And I'm pretty sure that about a quarter of you don't know why. So I'm going to be clear about why knowing that alpha doesn't tell me very much about this system, and why I wouldn't give you this question with any real follow-up. Well, I can't do what I wanted to, so fine. That's about the same size. The moment the object makes it to, say, here, will it have the same acceleration? Now take a moment and convince yourself why it will no longer have the same acceleration, and I will pick one of you to explain it to the class about what the use of the moment of inertia is. Are there any further questions on it? Okay. I'll have to do the same thing in 4th period, of course, but I want to talk about a more complex scenario now. But I'm really taking a step back with the example we're about to do. I want to look at the moment of inertia of a ring. So if we think back to us doing this yesterday, to calculate a moment of inertia, we are starting with this basic equation. It doesn't really tell us very much, but it reminds us that our job is to try to find a way of representing the mass of this object in terms of its geometry. To do that, I'm going to pick a place on the object and call it dm. But then I'm going to try and find a way of describing the mass of this object in terms of its size, in terms of its, in this case, I think we can still look at the length of the ring. And I'm going to use my point of reference as the center. That's going to be the axis of rotation. And this is a pretty straightforward example because the rod and the ring are really done the same way, because the ring is just a rod that's been wrapped in a circle. So let's assume a uniform ring. Let's also assume that we're dealing with the axis being at the center of the object. And lastly, let's consider that the object has a radius of capital R. I'm also going to assume that the inside radius and outside radius are close enough together that I don't have to worry about the thickness of the ring. That's not a great assumption because the inside of the ring clearly has mass that is closer to the center than the outside of the ring. So we always call this a thin ring example. And a thick ring example, we would have to take that into account. So we're going to treat this as a thin ring so that the inside mass is almost at the same distance away from the center as the outside mass. The thick ring example can be on the exam. So we will have to have a chance to talk about it. And for me, it's a great quiz question, practice question. So let's start by talking about what we have to do next. First, I recommended that you consider the type of way we deal with the density of the material. I think we can still use a linear density here, meaning I think we can talk about the mass per unit length of the ring. If I take a piece of it away, that length is an arc length. So I'm going to treat that length as if all of the lengths of this object have the same mass density. So linear density is given lambda. I'm going to assume the object has an entire mass m and an entire length 2 pi r. This would be the mass per unit length of the object. I am making this up at the start of the problem, meaning I wouldn't be given that. I'd be expected to come up with this placeholder. So that's our job, is to come up with a placeholder that can be used to be the density. This is so that I can convert dm into something else. I want to find a way of expressing dm in terms of the length of the object. So that's what I'm going to do next. I'm going to assume that this piece has a length that I will call ds. S is traditionally used for arc length. So assuming that that's an arc length of the object, I can write this as lambda ds. Any question about that? This is exactly how we did it yesterday. Here's where we're going to veer a little away from yesterday to set us up for our next example. That arc length can actually be expressed as an angle. And that's what I'd like to do. Is kind of say that I'm going to start at 0 degrees. I'm going to say that this point right here is 0 degrees, and I'm going out a little bit of angle. I'll say d theta. I have a reason why I want to express it in terms of an angle. I know how to add up the arc length by going around an entire circle. So that's why I'm going to choose to write this in terms of an angle, which means I need to express ds in terms of the angle. But if you remember, delta x equals delta theta times r. Do you remember that from a couple weeks ago? It tells me how far a point on the edge of a circle goes if I know how much angle is swept out. So using this analogy, I can say that ds is r d theta, or in the case of this problem, capital R d theta. Now, all of those steps were to try and find a way of expressing the geometry of the object. That's what that was all about. So that I can begin to assemble my integral in terms of something that's about geometry as opposed to something that's about mass. So I'm going to pull all the pieces together that I have. First, my integral symbol. Second, I'm going to use this for dm, lambda capital R d theta. This r squared is how far each piece of mass is from the axis of rotation. And in this problem, every piece is the same distance, capital R away. Right, that R is a placeholder to use for my particular geometry, but represents how far the piece of mass is. This piece of mass is a distance R away. That's a nice piece of mass, isn't it? I think I have a t-shirt idea. How far away is every piece of mass? You get it, right? It's subtle. Do you think they'll get it in the office? If we say it's a nice piece of mass. I was going to do something else. I've been working on a design, but the piece of mass, because I almost slipped and said something else. That is a solid mass. That's one thick piece of mass. I think there's a lot of ways we can go, but remember, it's about toeing the line, because now it's got to be approved. Or we'll just make them. Who cares? Yeah, I care. I like my job. All right. So I know that at this point, you're still wondering how this works. And part of me is going to tell you, you might never get it until you've done it a bunch of times on your own. And I can probably guarantee that not many of you went home and did the meter stick about its middle last night, even though I told you it would be a good practice. I'm trying to give you ways to go and practice, some things you can do that will help you. Your choice is going to be important here because I'm going to surprise you sometime by asking you to do something for me. So this is your second opportunity to really understand that I'm going to ask you to perform this for me without a net, which means no notes. Bring this all together and I get lambda r cubed d theta. Now, I have to assess my limits of integration. I want to add up every piece of arc. So I want to start at 0 degrees. And where do you think I need to go for this? Yeah?
2 pi?
Yeah, it's an entire circle, isn't it? So 2 pi seems like the appropriate angular distance to add up all the pieces. Any questions yet? All right, we are quite nearly at the end of this because lambda doesn't depend on where I am in the circle and r doesn't depend on where I am in the circle. So this becomes lambda r cubed. And now my integral is just 0 to 2 pi d theta. Now this is an easy integral. The integral of d theta with respect to theta is just theta. I know. But if I don't say that, I'm afraid I'll hear, where did the d theta go? So I think that becomes my my antiderivative. Theta evaluated from 0 to 2 pi. So all of this just becomes 2 pi lambda r cubed. That's my moment of inertia. But wait, there's more. We have to substitute in our original placeholder for the density, which will mean 2 pi times m over 2 pi r times r cubed, which produces the expected result. A hoop is mr squared. The 2 pi's cancel, one of the r's canceled, and I get the intended result, mr squared. Now, I'd ask if there's questions, but we went pretty deliberately slow. But I will be expecting you to do something similar to this. You know, I can see finding a moment of inertia of a hemisphere or a moment of inertia of a thick ring. or the moment of inertia is some other shape that uses some of the symmetry. So be aware, there's things to ask about. What's interesting is that what I can't do with this, and this is actually much harder, and I have some pretty smart math folks, what if I wanted to spin it like I'd spin a coin, or like some of you guys spin your rings on the desk? You guys know what I'm talking about? Through an axis like this way. That would be much harder. If you think about it, all of a sudden I got to figure out a way of expressing how far away this mass is compared to this mass or compared to this mass. They're not easy. This one's tough. Because each mass is a different distance away. It can be done, and there's a couple ways to do it. I'm going to write one of them up because I think you guys should see the range of this particular example. Somebody had to figure out how to do these. But, for the vast majority of you, this is probably the extent of what you'll need to know. I'm going to show you one more. And I'm going to do this one a little bit faster because you will not be expected to do this one. And the reason is because it's going to delve into some math that is probably outside of your abilities. But I believe it important for you to see it. That's not better. I want to do a disk. And part of the reason I want you to see a disk is because so far we've only seen one-dimensional examples, and the disk is two-dimensional. I know the ring feels like it's two-dimensional, but it really wasn't. It was still just a length. But this isn't. This is a two-dimensional object. And it's challenging to figure out how we're going to do this. I'm going to go through the same set of steps I did before. I'm going to start by identifying a couple of things. I'm going to do this about the center. I'm going to state that this object has a radius, capital R. It's important that we look closely at the letters I'm going to use this time because there's going to be a difference between uppercase r and lowercase r. I'm going to state that the whole thing has mass m, and therefore this is an areal density, not a linear density, an areal density, right? We'd call it a surface density. It's a mass per unit area. We use lowercase sigma usually for areal density. That's not super important. But it would just be m over pi capital R squared. Take the entire mass, divide by the entire area. That would represent the density of the object. The reason we're going to do it that way is we're going to pick out a single piece of mass. This is our dm. But our piece of mass is a piece of area, meaning dm is equal to the density times dA. Now I tried to draw this area as if it were a little rectangle. So I want to remind you some of the things we have to do in order to calculate the moment of inertia. First, I need a way to point to that piece so I know how far away it is from the axis of rotation. So I'm going to draw a radial to that object, and I'm going to label it lowercase r, because that lowercase r represents the distance from the axis to where that piece of mass is located. Now I know I drew it on one side, and I did that on purpose, because I'm going to call this little distance here dr, right? It's a little increase in r to represent how big that one side is. Imagine if I blow up this one little section for a second. What I really have is, I'm going to do my best to draw this so you can kind of get an idea for what I'm trying to do here. I'm imagining that R ends right here. So this is actually dr. And all of this is that rectangle that's right here. Everybody okay with what I'm trying to draw? Is that like I'm zooming in on that piece of the pie? Now, what I'm trying to say to you is that R points to where the object starts. dr is a little bit of like a delta. So I'm going out and saying that that length is a little more than R. Is that okay? Now, this length and this length, although are not exactly the same, they're pretty close in the way calculus works, right? Because dr is infinitesimally small. So these two lengths should be the same. And they're not really straight. They're kind of curved because they're arc lengths. I drew them kind of curvy on purpose. But this arc length would be r d theta. And I'm just going to fudge it and say that this side is r d theta too, and this side is dr as well, and that it's actually very close to a square. No, it's not. But remember, calculus allows us a little bit of the right to use the limit. And the limit gives us the ability to say that this is pretty close to a square. The reason that's important is I can use length times width to calculate the area. I can state that dA is dr, the length, times r d theta, the width. Now, I know you guys have never seen anything like this. It's okay. I'm not going to expect it of you. I just think you're smart enough to have seen this. So let me move on, because I'll run out of time otherwise. Aw, well, that's all got to go. I can get out of the way. And now we have dm equals sigma dr times r d theta. I know it's looking complicated. It's about to get more so. Because I is the integral of dm times r squared. Here's where it gets a little funky. That's going to be the integral of sigma times dr times r d theta times r squared. You'll notice there's two derivatives, which means I'm summing up two things. Give me a second. Look, there's two derivatives, so there must be two integrals. This is a double integral. I know you've never seen it before, or probably haven't seen it before. You will encounter this. This is kind of Calc 3 stuff, so it's a little outside the boundaries of Calc 2 and Calc 1, but it's the only way to use calculus to find an area. Now, generally, for something like this, it's not bad if there's no relationship between r and theta, and there's not. We're going to go from the inside edge to the outside edge, and we're going to go around the circle. So we set limits based on our object. Now, you have to go.